Good morning everyone. Myself Priji Bashaer and my colleague Bashaer will be presenting our project work on passive and low energy design of a country house in New Newton, UK.
We will go through these sessions to demonstrate our study.
Since 2014, buildings encompassing residential, commercial and public structures have consumed over 30% of the world's total primary energy supply. The residential sector has accounted for more than 65% of TPES consumption within the buildings. With these figures in mind, there is a pressing need to improve the total efficiency of buildings, particularly in light of projections indicating a 50% surge in the energy demand by 2050 compared to 2013.
Despite the obvious advantages, adopting passive and low energy design principles in New Newton faces challenges such as limited awareness, upfront cost, and regulatory barriers. Even so, these challenges present opportunities for collaboration, innovation, and policy intervention to create an environment helpful to sustainable development.
Under Paris Agreement, the European Commission has established a clear objective to reduce greenhouse gas emissions by at least 40% by 2030 and attain carbon neutrality by 2050. Enhancing energy efficiency stands out as an essential strategy in Paris Agreement.
Retrofitting buildings emerges as one of the most effective and economical approaches to meeting collective climate objectives.
In a study by Hunt et al. In 2019, the effectiveness of various energy-saving strategies were analyzed for a new development in Birmingham to provide a comparative study of different renewable technologies, aiming to provide an independent viewpoint for the decision makers to consider which technology to adopt for the best energy efficient design.
ASHRAE standard was established 25 years ago, but it was in commercial and institutional buildings, with less attention given to residential ventilation. As people have become more environmentally conscious, the publication of ASHRAE Standard 62.2 2003 occurred as the first nationally recognized standard on residential ventilation. The site selected for this study is in New Newton, near Birmingham in UK. New Newton is a traditional market town in the heart of the Midlands. River Ankle flows through the town centre and has extensive parklands on the south.
A residential plot of size 50 meter by 30 meter with the geographical coordinates latitude 52.5 north and longitudinal minus 1.4 is selected for the study. The average daily temperature varies from 2 degrees Celsius to 21 degrees Celsius. The town, which has warm summers and cold winters, has southerly wind during October.
For the remainder of the year, the wind is mostly from the west, peaking at 40% on January 6.
Figures represents the monthly average temperatures including daily means, minimum, maximums, as well as average high and low temperatures, daylight hours and wind direction of New Newton. The data was taken from Copernicus Climate Change Service. Data covers a period from January 2017 to June 2022.
In the base design, the proposed residential building called Green Villa is planned in such a way that the long axis in the east-west direction and the orientation of the house is towards south.
One of the basic passive design strategy is changing the building envelope. Characteristics of the building envelope play a crucial role in passive design. Shading devices, use of awnings, and overhangs to minimize direct sunlight exposure.
Daylight optimization for enhancing natural light utilization to reduce artificial lighting needs, and natural ventilation for maximizing airflow through strategic window placement for cooling.
Some of the passive cooling strategies during summer are use of natural ventilation. By arranging windows and vents to optimize the airflow patterns and capture prevailing winds, use of shading devices, install external shading elements like awnings or louvers to block direct sunlight and reduce the heat gain during the peak daytime hours, and use of reflective materials for roof so that the sunlight will be reflected back and the heat will not be retained.
Passive heating strategies during winter. Building sunroom and ground floor to use the heat during winter seasons. Maximizing glazing in the south and east side will increase the sun exposure. Integrate thermal mass materials such as brick, stone, or concrete into the building's structure. These materials absorb and retain heat during the day, gradually releasing it at night to help regulate indoor temperatures.
The proposed residential buildings base design and passive design strategies needs to be modeled in OpenStudio simulation software. Spaces, materials and thermal zones need to be defined. Defining the location and uploading the accurate weather data in standard formats will enable the software to perform the simulation analysis to evaluate the energy consumption for maintaining the comfortable indoor environment during all seasons of the year. Energy consumption for different strategies can be compared with the base design strategy and energy savings can be calculated.
For evaluating the efficiency of different passive design strategies, OpenStudio simulation tool was used. As a base case scenario, standard building model available in the software for mid-rise apartment was used. Steel framed exterior wall, steel sheet roof, and gypsum interior walls, carpeted concrete slab interior floor, and with insulation are the standard construction in this model.
As an alternate measure, base case 2 using construction with the thermal mass materials is also considered. In the base case 2, concrete block wall, concrete slab roof with roof membrane, tiled interior floor with carpet, insulated gypsum interior walls were considered. In the base case scenario, the villa is considered as south facing and simulations were done for 90, 180 and 270-degree orientations to find out the best orientation. In both cases, south facing scenario provides the best results. Also, it can be seen that there is a 5% reduction in the total energy consumption in the base case 2.
The base cases were further modeled for finding out the best strategy for heating during winter month. Improved glazing for the south and east walls, a sunroom in the southeast corner, and providing vents for windows to prevent the cold breeze from south were the strategies adopted for this simulation. The simulation results and 3D geometry modeled are shown here. From the results, it can be seen that providing sunroom and less glazing provided the best site energy utilization index EUI, but providing skylight for sunroom proved inefficient. Comparing to base case, the heating strategy with sunroom reduced the total site EUI by 5%. Hence, sunroom is considered as the best heating strategy.
For evaluating the efficiency of cooling strategies, overhangs for windows, an attic floor with shading, and operable windows for natural ventilations were considered. Allowing natural ventilation has proved inefficient. Providing an attic floor or plenum with a sloping roof is found to be the most energy efficient strategy. This strategy has reduced the total site energy utilization index by 25% from the base case. Hence, providing a plenum or attic floor with sloping roof is considered the best cooling strategy for the site.
From the above simulation results, the optimal solutions was arrived with thermal mass construction, sunroom without skylight, minimum glazing, overhangs, vents for windows, fixed windows, attic floor or plenum with sloping roof and deciduous trees in the south and west was selected as the optimal solution. A sloping roof without plenum strategy and window with only overhangs and no fence were also modeled and compared. From the results, it can be seen that the optimal solution considered is the most energy efficient one among all the 25 different scenarios simulated.
Open Studio Data Viewer will help us to see graphically the energy requirement and its connection with the outside weather conditions. This graph shows outside air temperature and the corresponding day heating or cooling energy required.
A comparative study of energy requirement for various scenarios are done as shown in the table here. It can be seen that there is a saving of 18% in the total site EUI compared to the best case scenario using ASHRAE specified construction for zone 5. When heating energy requirement only is considered, the saving is 28% and for cooling only it is 1%. But when the optimal case is compared with the base case 1 of this study, there is a saving of 37% in the total site EUI, where 34% of this is in the heating energy and 52% is in cooling alone.
New Newton follows BREEAM, Building Research Establishment Environmental Assessment Method, as a rating system to measure environmental performance of new and existing buildings. BREEAM was established in United Kingdom in 1990 under the support of the British Research Establishment.
BREEAM assessment uses recognized measures of performance to evaluate the building specifications, design, construction, and use. These measures are set against 9 categories including energy, management, health and well-being, materials, transport, water, waste, pollution, land use, and ecology.
Category weighings are fundamental to any building environmental assessment method, providing a means of defining and ranking the relative impact of environmental issues. BREEAM uses an explicit weighing system to determine the overall BREEAM score.
The table represents the score needed to achieve desired BREEAM rating. The figure in this page shows the weightages for each subcategory. The outstanding rating means it's an innovator. Excellent is for best practice. Very good means advanced good practice. Good means intermediate good practice. And pass means standard good practice.
The BREEAM score for the optimal design proposed has been evaluated as shown in table with overall score of 55.3%, certified as very good.
In conclusion, passive house design represents a typical shift towards a more mindful, resilient, and environmental friendly, responsible approach to architecture.
As we struggle to build a sustainable future, passive house principle serves as a guiding light, illuminating the path towards a greener and more sustainable tomorrow. Thank you for your time.